Okay, when we're working with the inverse trigonometric functions, the calculus that we're going to do is very similar to the calculus that we've been doing. We just have some new rules. So we know how to deal with sine, cosine, tangent, so on. Okay, we're going to do exactly the same thing here, but with new rules. Okay, instead of the sine inverse's derivative being something to do with cosine, it's actually not anything like that at all, is it? Okay. So before we do that, though, I want to talk about just inverse functions in general. Okay, if we have a function y equals x squared, for instance, okay, and we restrict the domain to be x greater than or equal to 0, so in other words, we just take the right half of the parabola, okay, its inverse, okay, is going to be reversing the x and y and then solving for y, and if we do that correctly, we're going to get y equals radical x. Normally, when we take that square root of y, we get plus and minus the square root of x, but again, we're talking about a domain greater than or equal to 0 only. Okay, which means that we're just going to get the top half of the sideways parabola, if you will. Okay, remember a couple other features with functions that are inverses of each other. Geometrically, if we were to graph those two, they would be symmetric about the line y equals x. Okay. Another thing that they have is that if we have an xy chart for the function, okay, which we can certainly make for this case, 0, 0, 1, 1, 2, 4, and 3, 9, okay, the inverse function should have the reversed coordinates. So therefore, we should have the points 0, 0, 1, 1, okay, 4, 2, 9, 3. Okay. All right. And ultimately, that kind of leads us to the algebra part of how we can get from function to inverse. Okay, we switch the x and y, okay, and that gives us the inverse. The only reason that this is not a function right now is because it's not solved for y. So if we solve it for y, now it becomes a function. Okay. All right. Now, what it boils down to is that for our purposes, when we deal with any function and its inverse, okay, there's a relationship between the function's derivative and the inverse's derivative. Okay, and so let's start with this one. So if f of x is again our x squared function, we know that it goes through the point 2, 4. We know the derivative of f of x is 2x. Okay, then we can find the derivative at 2, and that would be equal to 4. If we plug our 2 in there, we're going to get 4. And if you look at the picture, I plotted that point here. That point 2, 4 is right there. If we were to draw a tangent line right there, it would match up, with our 4 derivative here. Fairly steep, if you will. Okay. And here's what the relationship is, okay, between function and inverse derivatives. Okay. The first thing you got to recognize is that the relationship, okay, between these derivatives is at corresponding points. All right. So there's a relationship at corresponding points, not at the same x value necessarily. Okay? So at f of 2 and f inverse at 2, those are not necessarily corresponding points. The only way they would be is if they were 2, 2 and 2, 2. Okay? But at corresponding points, if we know the derivative of f at 2, okay, then we can find the inverse's derivative at 4. Okay? Because that's the corresponding point to 2, 4 with these two functions. Okay? So ultimately, okay, I could answer this question without having to even find the derivative of the inverse, because I already know the answer. But just say we did find the derivative of the inverse, which we can certainly do in this case. Okay, we can't in all cases. Okay, sometimes it's difficult to find an equation for the inverse. Okay, and if we can't find an equation, then it's going to be difficult to find the derivative. True? Okay. All right, so let's see what the relationship is. Then if we again, we're putting the 4 into this because we want the derivative of the inverse at the corresponding point. If we plug a 4 in there, we're going to get 1 over 2 times 2, which is 1/4. Okay? And this is an illustration of the rule here. Okay? The rule is this. At corresponding points, okay, the derivative of the function and the derivative of the inverse are reciprocals. Okay? And again, you can see that in the picture up here above, if I go 4, 2 right there, you can see that the slope is certainly a lot less than it was on the other corresponding point I pointed out. Okay? It's got a much less steep slope there, so therefore our slopes are always going to be reciprocals of each other at corresponding points. Now, keep in mind that at 0, 0 and 1, 1, if we were to find the derivative of both at those 2 points, they'd be the same because ultimately the corresponding points are both 1, 1. Okay? All right, so that's one element of dealing with inverses. Okay? We can see I made a little pattern over here. I did it with 3, 9. Of course, the corresponding point would be 9, 3. And notice again, I'd get 6 and 1/6. Okay, 1, 1 is, I think I said the same, but I meant reciprocals anyway. But regardless, at 1, 1, it's 2. Okay, and the reciprocal is 1/2. Okay, So again, whatever the function's derivative is, at the corresponding point, the inverse has a reciprocal derivative. All right. So, for instance, I'm going to give you another example here. I have y equals e to the x. Okay. That goes to the point 2e squared. Okay. And I'm going to tell you right now the derivative at y at 2 is e squared. Okay. Now, again, knowing that the corresponding point on the natural log function, which is its inverse, is e squared 2. Okay, we should be able to tell what's the derivative at that point. Okay, without even knowing how to find the derivative of ln x. Okay, because according to our pattern here, what should it be? Okay, it should be 1 over e squared. It should be the reciprocal, and it is. And again, without knowing how to find the derivatives of either necessarily, okay, being given enough information, okay, we can do that based on that relationship. And again, the relationship is when we have inverse functions at corresponding points, okay, derivatives are reciprocals of each other. Okay. Questions so far on that part? All right, so the other part is we're going to be dealing with our inverse trig functions, because sometimes the functions we have are going to be in terms of inverse sine, cosine, tangent, so on. Okay, so the first thing we're going to learn is the actual rules here. Okay, if we were just to be given the sine inverse of x, okay, the derivative is going to be 1 over radical 1 minus x squared. Okay, all right, and again, these are going to be on the non-calculator parts of the AP test. Okay, so therefore these need to be memorized. Okay, the good news is there's only 3 to memorize instead of 6, though. Okay, and I'll tell you why in a minute. So sine inverse is 1 over 1 minus x squared and under the radical. Okay, now the chain rule version of that, okay, is as follows. This is what you'll see in your book as well. If we have the inverse sine of some function, whatever that function may be, okay, then we're going to find the derivative by doing 1 over 1 minus, or 1 over the square root of 1 minus u squared. So whatever that function is going to go in as normal, okay, just like any chain rule problem. And then this represents the derivative of the inside function. Okay, so we'll find the derivative of the inside, okay, and we'll multiply those two together and we'll get a result. Okay. All right, so as an example, I used sine inverse of 2x squared plus 4x. So if I recognize that's in the form of sine inverse of u, okay, I'm going to do 1 over 1 minus u squared in radical. Okay, I also multiplied it by the derivative of u, which is the inside function. Okay, and then that's just a matter of putting the u in where it belongs. Now, one question is, do we need to do anything with this? I mean, if we were to expand that and then have 1 minus that, is there going to be any way that anything is going to come out of the radical there? No. So again, no sense in doing anything more with that algebraically. Okay. All right. Now, we're going to look at next the tangent function. Okay, tangent inverse, that is. So once again, if we have the tangent inverse of any function, okay, the derivative is 1 over 1 plus u squared times the derivative of the inside function, which is the du dx part of that. Okay, so that's going to be our rule for tangent inverse. Okay, and so my example, I used a tangent inverse of sine x. Okay, again, recognizing that tangent inverse is the outside function, I would write my u down as sine x, my y is tangent inverse of u. Okay, so therefore my tangent inverse derivative is the same as what I just wrote for the rule. Okay, the du dx in this case is cosine x. Okay, and then it's just a matter of filling in the blank here with our u. And if we do that, we're going to get cosine x on top, 1 plus, again, it's sine x all squared, which we can write as sine squared x. Okay. Right, so again, the chain rule part of this is just applied the same way that we've been applying it with the other functions we've learned about. Okay. But the key is we just need to make sure we know what the correct rule is for each of these trig functions. Okay. All right. Now, before I go on to the third one, I want to talk about there's a cofunction identity, okay, that connects the cosine inverse and the sine inverse, and this is why we only have to memorize 3 instead of 6, because if we use this cofunction identity, okay, and we implicitly differentiate, okay, if we differentiate the left side, we'd have the derivative of cosine inverse x, and that's what we're interested in to find out what that is. Okay, the derivative of pi over 2 is 0, minus, what's the derivative of sine inverse? We already know the rule for that. True? Okay, and so therefore, what's the derivative of cosine inverse? It's the opposite of what the sine inverse derivative is. So again, if you know the sine, then you also know what? Okay, you also know the cosine inverse. Okay, because it's always just going to be the opposite. Okay, and lucky for us, the tangent inverse has a similar cofunction identity, okay, which will lead us to the fact that the derivative of the cotangent inverse is just the opposite of the tangent inverse. So once again, if you know the tangent inverse derivative, okay, you really know the cotangent also because it's just the opposite. Okay. All right, and we can do the same thing with secant. Okay, secant u's derivative is the absolute value of u on the bottom times the square root of u squared minus 1. Okay, that's the general form when again u can represent any function. Okay, so we'll apply that the same way as we did the other two. Okay, and then of course the derivative of the cosecant inverse, okay, is just the opposite of that. Okay, it's the negative. Okay. Questions so far? Great. Alright, just for argument's sake, we're going to look at the problem here just so we can look at the algebra here of the cosine inverse. Okay. So if we have cosine inverse of 1 over x, okay, I would first recognize that my inside function is the 1 over x, and my outside function is the cosine inverse of u. Okay. And when I do the math on that, I'm going to write down the cosine inverse definition, okay, derivative, if you will. And then this is the derivative of u, if you will. This is the derivative of the inside function. Notice I did that over here. I wrote it as a power function and then used the power rule, and then wrote it back in its other form. Okay. Now the problem we run into with this is when we replace that u with what u is equal to, okay, we wind up with a fraction here in our radical. Okay, and so that makes it a complex fraction, and I'm pretty sure that the computer is not going to accept a complex fraction, nor am I. Okay, so what I want to talk about is the algebra of this. Okay, what are we going to do if that happens, if we wind up with a complex fraction? Okay, so what I did over here is I just took the radical. Okay, I'm just looking at the radical only. That's the problem. We have a fraction underneath this radical that we need to deal with. Okay, so the general strategy here is going to be to get these two together. Okay, so if we get them together, we need a common denominator, of course. So the 1 can become x squared over x squared minus 1 over x squared. Okay, and if we put those two together, we're going to have radical x squared minus 1 over x squared. Okay. And once we do that, then if you notice the bottom is a perfect square. True? So if that's the case, then we can take that right out. We can split those into two different radicals. Okay? And then we can take that out. And by taking that out, you can either write that over x or you can write 1 over x in front of it. Okay? Either one of those is fine. But keep in mind, though, that some people usually mess this up by just putting an x in front. But remember, the x right here doesn't come out on top of the fraction. It comes out where? It comes out on the bottom. Okay? So if somewhere on the side you simplify the radical part, okay, and then plug it back in. Okay, here's where I plugged it back in now. Okay, and you notice that now that that's out, what's going to happen with these two? Okay, the two that are out can reduce. We got an x squared and an x. Okay, so ultimately, what do they make together? X times still have x squared minus 1. Okay, so that's the algebra that it's going to take to simplify that and make it not have a complex fraction portion. Okay. Okay, questions so far? Okay. All right, so the majority of your problems that you're going to be doing are going to be just working by using those definitions. Okay. All right, so we're going to work on those, continue to work on those for tomorrow. Tomorrow we have a day that we're going to be working on reviewing, getting ourselves ready for the quiz on Friday. So we'll have most of the time to ask questions and work on problems and make sure that we're good to go on this. Okay.